24, Doktor.
Barulah complete. So, sekarang dah ada seorang terkeluar pula. Okay, doesn't matter. But anyway, so thank you very much to all of you, Mr. Azwan, especially the class rep. So without further ado, we will start our class with the recitation of doa. Can someone please volunteer?
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين حمدا يوافي نعمه ويكافئ مزيدا يا ربنا لك الحمد كما ينبغي لجلال وجهك الكريم وعظيم سلطانك اللهم صل على محمد وعلى آل محمد اللهم اغفر لنا ذنوبنا ولوالدينا وارحمهما كما ربيانا صغيرا اللهم اجعلني في
في
قلبي
قلبي
نورا
نورا وفي
وفي
لساني
لساني
نورا
نور
وفي
وفي
بصري نورا
نور
وفي سمعي
وفي
نورا
سمعي نورا
عن
وعين
يميني نورا
نورا
عن
وعين
يساري نورا
نور ومن
ومن
فوقي
فوقي نورا
نورا
ومن
ومن
تحتي
تحتي
نورا
نورا ومن
ومن أمامي
أمامي
نورا
نورا ومن
ومن
خلفي
خلفي
نورا
نورا
واجعل
واجعل
لي
لي في
في
نفسي
نفسي
نورا
رب اشرح لي
رب اشرح
صدري
لي
ويسر لي
صدري ويسر
أمري
لي
واحلل
أمري
عقدة
واحلل
من
عقدة
لساني
من
يفقهوا
لساني
قولي
يفقه قولي.
اللهم افتح علينا حكمتك وانشر علينا من خزائن رحمتك يا أرحم الراحمين سبحان ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
Amin, 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 ya Rabbal Alamin. Thank you so much to Mr. Akasha. So without further ado, we will start our class. So you will keep turning on your camera because I will watch you, not watch tu nampak macam kodeng lah pula kan. I will see you on the second screen, yeah. So keep it till the end of the class. I'm going to share my PowerPoint slide now. Okay, you should be seeing my PowerPoint slide now. Can you? Right? Just
Doctor.
yes, very good. Thank
Nampak.
you, Azri. Yes, thank you, Azra and Shafika. Thank you so much. So I am going to go straight to the last slide that we have covered, which was on the case number 1. Okay, so this is where you stopped. Oops. All right, we were talking about maximizing the desired products. I'm going to go back a few slides before. We are looking into the first kind of reaction, which is parallel reaction. After we have covered all those cases here, case 1, 2, 3, 4, then we will go to the next kind of reaction, which is the series reaction. So let us first look at the parallel reaction. So you should already know what is parallel reaction. Which is shown on this slide, showing you 2 reactions with one reactant, yeah, one reactant A. The first reaction produces the desired product. The second reaction produces the undesired product. So we know that if we want to maximize the production of the desired product, which we use capital D here in this case, we analyze the data, or we set the requirement for the reactor specification by setting high selectivity. Yeah, the selectivity is written based on the ratio of the rate of formation of the desired product against the rate of formation of the undesired product. So we know that we have written all the respective equation for both rate of formation for both products. And finally, this is the simplified, not to say simplified, but the resulted equation, which we can use mathematically by introducing increase or low or high concentration or intensity of something. So we have three parameters here. The first one is the KD, the second one is the KU. Both Ks are representing the specific rate constant for the desired and undesired product respectively. And thirdly is the concentration to the power of A. Here we introduce this A, which is the alpha 1 minus alpha 2, which you could see clearly from the resultant equation, having that exponent formula. So to simplify it, we simply represent it by A. Yeah? If we say from this case number 1, the alpha 1 is greater than alpha 2, then we can simply easily say that the resulted formula would give you a positive value. So the A is greater than 0. From here, let me erase my scribbling here so that we can easily make a conclusion what to do. Yeah, if we want to ensure that the selectivity is greater or selectivity here is higher. Oh, my pen doesn't come out, so hold on. Saya padam, rupanya saya kena go back and share again. So here, now only I can write. Yeah. So we know that we want to make sure that the selectivity is high. So from this, mathematically, we can say the KD is also high. The KU must be low. The concentration of the limiting reactant A, which is only one reactant here, must be high. Then we use the resultant requirement from our understanding to choose which reactor scheme which is going to be the most suitable to increase the production of the desired product for these two parallel reactions from one reactant. Yeah, so we look into two kinds of phases. If for gas phase, if we want to have high concentration of A, so we follow the ideal gas law. Therefore, the pressure of the stream must be as high as well. Yeah. In other words, not in other words, additionally, to ensure that the concentration of the limiting reactant is also maintaining to be as high as well, we are going to avoid using inerts. Yeah, so we can introduce without inerts to the feed stream. Yeah, with high concentration and no inerts, then the concentration of the feed stream inlet is high. Yeah, when we are dealing with the gas phase. If we are dealing with the liquid phase, then since we want this concentration to be as high as possible, since it is liquid phase, we need to prepare it to be in liquid phase. Yeah, diluent is needed. In this case, to ensure that the concentration of A is high, so the diluent must be kept as low as possible. Yeah. Then the other decision that we have to make for liquid phase, normally we can use batch or CSTR. So we have to make a choice with either batch or CSTR. Since CA must be set to be as high as possible, so we avoid using perfectly mixed CSTR because fundamentally, in a perfectly mixed CSTR, the concentration is always at its lowest. Yeah. So in that case, we choose batch for liquid phase. By right, the CSTR with inlet stream and also outlet stream is actually a batch. Yeah, but a batch with a continuous inlet. For batch reactor system, let me rephrase, it's a batch reactor. So for a batch reactor system, of course, we don't have inlet and we also don't have outlet. Yeah, but it's the same thing. It's just a matter of flow streams entering or exiting the reactor. All right. So this is clear for case number 1, which we have covered last week. We are going to proceed with case number 2, whereby the alpha 1 now is lesser than alpha 2. So we're going to go and have a closer look on the equation of the selectivity. From here, we set that exponent by B. Earlier, we used A, alphabet A, and now we're going to use alphabet B. When we set the alpha 1 is, not to say we set, when we know that the situation, the alpha 1 is lesser than alpha 2, yeah? So therefore, we are going to set the equation as reverse, whereby alpha 2 minus alpha 1. Why do we do that? Because we want to ensure that the exponent b here is positive. B is greater than 0. Yeah. So when we write the equation here, we have the alpha 2 minus alpha 1, which is positive value. Alpha 2, of course, alpha 2 here is lesser, right? This is greater alpha 1. Yeah, correct. So this is alpha 1 is greater. Since it's negative, then it's still at the denominator. Yeah. So we have the simplified equation for the selectivity. When we want the selectivity to be as high as possible, so we need to ensure that the concentration of the B to be as low as possible. Ku also low. KD is high. Do you have any question here? I'm afraid that how I presented just now is confusing. This takes 1 minute to have a look at this equation if I explain it confusingly just now. So have a look again. Look at the alpha 1 is lesser than A2, alpha 2, alpha 1, lesser than alpha 2, right? Then this one would be here, negative. So alpha 2 is greater. Understand? Right? Faham?
Faham.
Very good. So now with that resultant requirement, we are going to choose the best reactor scheme, whereby when we set the concentration of the limiting reactant is to be as low as possible for gas phase, according to the ideal gas law, the pressure is going to be low, right? To ensure low concentration of the A. Yeah. Again, additionally, if we want the A to be as low as possible, we are going to introduce inerts so that the concentration is also low. Relatively, when you have inerts, when you have A, then the A will be reduced in comparison to only pure A. All right, so this is what it means. For the liquid phase, since you want the A to be as low as possible, so we are going to choose fundamentally the CSER, and also the A is diluted, by using diluents, and in this case, the diluents is always inerts, because we don't want the solvent or the dilute, which is diluting the Ca, reacts in that reaction. It should not react together. That's the purpose of diluting it. So in this case, the best reactor scheme for case number 2 is the STR. All right, so we are going to go to the next case. Now, the next cases are cases number 3 and number 4, which is the example of the effect of temperature, on the selectivity. So it means that during the reaction, the temperature changes. So due to the change of temperature, we need to apply the Arrhenius equation. And due to that as well, the activation energy will also change. So we have 2 cases. Let us start with case number 1, whereby the ED, which is the activation energy, is greater than the activation energy of the desired product is greater than the activation energy of the undesired product. So I'm going to go to the next slide. All right. So this slide is just a basic thing showing you two cases. Yeah. Case number 4, the activation energy of the desired is now lesser than the activation energy of the undesired. Yeah. So I put a question there. What is the temperature relationship towards the selectivity? Yeah. Due to the effect of temperature, we apply the Arrhenius law. So we write both equations using the Arrhenius law for the desired here KD and the undesired, which is the KU. So we have two equations there. We simply relate it by making a ratio of KD over KU, and finally you could see that the ratio of KD over KU is written as such, yeah, whereby the AD is the frequency factor of the desired, AU is the frequency factor of the undesired. Now, so please take note of the unit used for the activation energy here for the desired and undesired, which are both kilocalorie per mole. So please take note that activation energy, which you may have seen earlier in our previous topics, are normally written as joule per mole, yeah, joule per mole, or maybe kilojoule per mole. It could also be written as kilocalorie per mole, yeah, to represent the activation energy. Of course, the alpha 1 and alpha 2 has no units. The R, yeah, here we have the exponent there. We have activation energy, the universal gas constant, and the temperature. Temperature is always in Kelvin because it's considered as the absolute temperature. The R unit, so here look at the R. It says there refer to table. So which table? So you're going to look at the table from the end of your textbook, which is the appendix for the universal gas constant. So I wrote there refer to table because here we use kilocalorie per mole. So therefore you need to use the most appropriate units, which you can cancel out the units, yeah, according to calorie. If you use joule per mole, then of course you have to use a different value of R accordingly based on the unit available, yeah, joule per mole. I hope you understand on that, yeah. Please, if you don't, flip your textbook and go to the end of the textbook. You could see the various values for the R available according to the different units. All right. Yeah, so for this case 3, since ED is greater than EU, so if we follow this formula, the selectivity is equivalent to that whole formula, knowing the exponential factor value. So we plot in the values in, and we know as the temperature increases, as it goes to your right, the selectivity increases as well. So this is applicable when the activation energy of the desired is greater than the activation energy of the undesired. It means here when temperature increases, factor exponent, this whole thing also increases, which therefore the KD and S increase. Yeah. So if you go to the next page, the next slide, showing you where the ED, the activation energy of the desired, is now lesser than the activation energy of the undesired. So knowing the exponential value factor values, we know that as the temperature increases, the selectivity decreases. So if we want to have a selectivity of a higher value, then the temperature would need to be decreased. Yeah, in this case, for ED lesser than EU, then when temperature decreases, the factor exponent increases, therefore the KD and the selectivity increases. KD and selectivity increase. Yeah. So this is plotted based on the known value of the formula itself. All right. Now, let us read the last sentence which I wrote here. The selectivity can be related to RA, which is rate of reaction, which is directly proportional to the case. You know the R is equivalent to K and C. Therefore, the selectivity can be maximized relevantly to cases 3 and 4. Yeah. So, so this is just a statement saying that we can use selectivity with relevant understanding, yeah, to maximize our desired product. Okay, the next one would be the slide which you have seen earlier last week. To maximize the D, one of the way is to adjust the concentration. And once you do that, of course, you can make a decision of which reactor scheme to be the most suitable. Yeah, so we're going to go to here. And this additionally giving you more information of other criteria for reactor selection. You know that you have to choose the reactor which is most suitable for your reactions. And we have learned earlier before this slide, one of the way is to refer to selectivity, and we did that. Other than that, you can also use yield or temperature control, and also very important here, safety, because you have to decide which reactor to choose. Not only because of the selectivity, you should also look into the safety side. And finally, the cost. So these are the 5 criteria which you need to consider in deciding the final decided most suitable reactor scheme, yeah, for your reaction. So on this slide, you could see that we have covered on the left-hand side with one reactant producing either the D or also the U. Now we're going to proceed to the next condition, which is rather than having one reactant, the reactants are now 2 reactants producing the desired and also the undesired products. All right, so we're going to go to the next slide. Maximizing the desired product from 2 reactants. Now, if you look at this slide, you could also look at the other slide. Yeah, we have other slide showing you basically the same orientation of different collections of reactor system. Yeah. If you go to the previous slide, the figure looks a little bit unclear because of the small writing. So I'm going to go to the second slide. Yeah. In my previous class, I did use this slide, and for my second class today, I'm going to use this slide. Yeah, it's the same thing. The only difference is that this slide is taken from the 5th edition of Fogler. The previous slide is taken from the 4th edition of Fogler. So they are the same. It's just that Mr. Fogler has upgraded the quality of presentation of the collection of reactor system, right? So I'm going to use this one from the 5th edition of Fogler. We have various collections starting from A until JK, L. Yeah. So how many? L nombor apa? L berapa? Okay, 10 nombor apa? 10 apa?
12.
12. Kalau 10 je lah. Lupa dah. All right. Very good. So we're going to start with the A. Now, take note that we are looking into, instead of 1 reactants, now 2 reactants. Yeah, 2 reactants. So look at all the orientation. We have 2 reactants. Here we have batch. Of course, you simply put in the 2 reactants, then the D semi-batch, 2 reactants, the semi-batch, 2 reactants, 2 reactants, 2 reactants, 2 reactants, 2 reactants, and 2 reactants. So at my place, Azan is it's. I heard the Azan. I'm hearing the Azan, so I'm gonna take a few minutes break first. Yeah. So that's your place. So let us just stop for a while. So I am back now. I hope you are also back at your places. So please turn on your camera. Okay, we are going to continue with the maximizing the desired product from two reactants. As you see that from A till L have two reactants as your feed stream, yeah? Either in one feed stream or in two separate feed streams. And why do we have such configuration? Why some reactors having the A and B in one pipeline, or maybe in one feed stream, and the other one has to be fed separately. Yeah, there are reasons for that. So first, before we do that, we are going to understand each of the configuration or the arrangement. Yeah, so let us start with the A. The A is a CSTR. Of course, you have the impeller there or agitator. Then you have two different streams, yeah? One stream feeding the B, second stream feeding the A, yeah? Then the outlet stream is only one producing the D and the E. So that is A. Let's have a look at B. We have two different streams as well, supplying the A and B respectively or separately in a tubular reactor with one outlet stream, yeah, having both the desired and the undesired. C is simply the batch whereby if you have two reactants, then you have the two reactants already fed in the batch, no continuous feeding in or continuous exiting, yeah. That is batch. D and E both are semi-batch. Why is it called semi? So semi, because we have one, the first stream for the D configuration, the first stream is pure A, being fed initially to the batch reactor. Then later on, the B is added, yeah, to the batch system, yeah. So we call it semi-batch. The E is simply now not the A as pure, but the B as pure, which is initially added to the batch reactor, and later on A is added in a different separate feed stream. Yeah. So let us go to F and G. Both are membrane reactor. Both have A and B with two different feed streams. But in F, the A is fed directly to the tubular reactor, but the B is fed not only as inlet but also as side streams, yeah, with side streams, which is added at a different time or different position. While G, instead of B, instead of A, here in F, A being fed to the reactor, now B is being fed to the reactor, and now the A is also fed at the side streams. Yeah. So those are the two differences. Yeah. Either A or B becomes the side streams added to the tubular reactor. In this case, membrane reactor. All right. Next, H, a series of small CSCR. If you decide to run your production in a series of CSCR, so we still deal with the two reactants. The first one is the A being added to the first reactor. Then consecutively, the outlet will become the inlet to the next reactor until the third reactor here. And finally, one outlet stream, yeah, having both desired and the undesired. But here, we have a separate stream of B, which is being added separately to the reactor, yeah? to the first one, to the second one, and to the third one. All right, we're gonna have a look at the further slides later on to understand why is this being said as such. Yeah. So let us proceed with the I configuration. Here we have A and B being fed together to the tubular reactor, producing one outlet stream having the desired and undesired. Now we decide to create a recycle stream from the outlet stream, so we recycle it to the inlet stream. Why do we do that? So we're going to have a look at the further slide why this recycle stream is created. Yeah. Of course, you have this symbol. That symbol is for the heat equipment, either to cool it down or to heat it up. So we're going to have a look at the further slide proposing in which kind of reaction which is suitable to have this recycle stream. The J shows you rather than the tubular reactor, but now the CSCR reactor has the recycling stream. Yeah, the same thing, it's just that the change of reactor type. The next one is the membrane reactor. Here it's a tubular kind, but we have membrane inside of it. The A and B are added together, producing one outlet stream having both the desired and undesired. But we decide to take out another product, meaning here A plus B produces C plus D. Yeah? So here is simply the notation that you use for desired and undesired. Yeah? The CABC is simply the notation that you use to indicate different components. Yeah, so we decide during the tubular reactor along the membrane reactor, tubular having the membranes, we want to take out the C. So the question would be why? Why do we do that? So we're going to have a look at the further slides later on. Lastly, it is called the reactive distillation. Simply because we have the A and B being fed to the batch reactor having the impeller, then during the reaction it produces some sort of gas, C, and that component is taken out. It's just like the K, yeah? K and L is just like the same, yeah, having one outlet stream containing the D and the U. In this case, we can say that it's a gas liquid system, yeah. The A and B, then the C could be assumed to be gas, so it's taken out. Logically, the light gas will go up. It's just a matter of purging the gas out during the reaction using this reactive distillation. All right. So we're going to go to different cases with different proposal of the reactor, yeah, for two reactants. Again, it's a parallel reaction, yeah. So for the first case, we have two reactants there, and both reactions are in parallel. And it says that for case number 1, the alpha 1 is greater than alpha 2, and the beta 1 is also greater than beta 2. So we're going to go to the next slide, showing the full equation. Of course, one of the criteria that we choose to make a decision of which reactor system to be selected is selectivity. Remember, we have 5 criteria. So we're just going to focus on the selectivity. So if we choose selectivity, then we need to know the formula written for such cases, yeah, with the two reactants. So this is the resulted formula having the KD and KU. KD is simply here, KD, KU is simply here, KU is the same thing, yeah. So we have two concentration, A and B, of course, to the power of the exponent, right? So we have CA. I'm going to go to the next slide. The CA to the power of that exponent, CB to the power of that exponent. To make it simplify, we replace that formula by small a and that formula by small b. In this case, you can easily mathematically decide that if you want to have high selectivity, the CA and the CB must be both also high. All right. Why? Because simply of the A and B, both are positive. The A is also positive, the B is also positive. Why? Because both the alpha 1 and beta 1 are greater than the other alpha and beta, respectively. All right. Knowing that resulted requirement, we know that we should have a concentration of B and A to be at its maximum level. For gas phase, then high pressure, and then high concentration. So we minimize the use of inerts, yeah, in this case. So we're going to go to the next slide to show you the proposed reactor scheme for this case number 1 for 2 reactors with that specification. In order to have high concentration of both the A and B, so we're going to use batch system rather than CSCR. And alternatively, you can propose tabular reactor whereby at the initial time, the concentration of the A and B is also are high. Yeah, so that would be the proposed reactor scheme. Right, we're going to go to case number 2. Before I proceed, do you have any question? Faiz? Faiz geleng, tak nampak muka Faiz. Rambut you menutup sebelah mata you. Cuba turun kamera sikit. Tak nampak. Turun lagi, tak nampak. Oh, baru nampak misai. Tak nampak lah Faiz. Turun lagi. Turun lagi kameranya. Baru nampak Faiz. Tak ada soalan Okay, Azri. Ada tak ada? Daniel.
Saya madam.
Daniel tak ada, Azri tak ada. Daniel. Najwa. So masa saya duk panggil-panggil nama ni kan, so why not you ensure that you are also at the large gallery preview so that you could see your classmates ya. So kamu tahulah saya duk tengah susun-susun nama nak sebut siapa. I don't know whether the orientation is the same or not. Shadiana, do you have any question Shadiana? No. Hanani, cantiklah background. Hanani. No. Mashita. No as well. Yes or no? Mashita.
Yes, Doktor.
Ada soalan? Mic not working ah. Okay, please check. Nanti nak nyanyi tak ada mic macam mana? Syafiq. Muhammad Syafiq. Mana ni ke dua Syafiq? Muhammad Syafiq Abu.
Tak ada doktor.
Tak ada. Najwa.
So far no doktor.
So far okay? Familiar? So tak ada soalan sebab beradam lah ni.
No, Doktor.
No doktor. Okay, Camelia. Atricia. No. Mic tak okay? Mic tak okay? Okay. Nurin.
Doktor, saya ada soalan.
Okay. Ada soalan. Nurin.
Yang untuk inerts tu kan, dia kata minimize kan. What if kalau kita tak insert any inerts, boleh ke tak? Ke kena ada
Kat mana?
inerts juga?
Di mana?
Yang point number 3 tu.
On this slide, yeah? You mean on this slide?
Yes.
Okay, so our resulted requirement is to ensure that the concentration of A and B is to be high, right? Okay. Some of the cases, very good question here, Nurin. Some of the cases, we cannot avoid having inerts. Yeah, we cannot avoid having inerts. Just that to ensure that the concentration of the inerts or relatively the concentration of the limiting reactant or the reactants are to the inerts tadi saya sebut apa? Saya takut salah sebut. The relative comparison between the concentration of A and B to the inerts are high, meaning CA over inerts high. Maksudnya inerts tu rendah. There are some cases tak boleh avoid inerts, so we can ensure that as minimum as possible of the inerts. But if you can avoid having inerts, then to have high concentration of A and B, then it's also possible, right? Do I answer your question? Yes, thank you. S1. Hello, hello? Hello, S1?
No,
Microphone
Doktor.
dah cantik dah? Tak ada Okay,
Ada.
thank you. Thank you. Amira?
Tak ada, doktor.
Very good. Anis?
So far no, doktor.
Okay, Mirza.
Setakat ni tak ada, doktor.
Ya, Afifah?
No, doktor.
No. Fazlika?
No, doktor.
Umaira?
No, doktor.
Najwa?
No, doktor.
Okay, Nur Nada?
Tak ada, doktor.
Okay, Alia?
For now, not yet.
All right, not yet. Very good. So I'm waiting for your question then. Azri?
No, doktor.
Dia sedap sangat you punya suara. Tak dengar. Apa?
No, doktor.
No, doctor. Okay. Daniel?
Ya, tu.
Daniel?
No, doktor.
Okay, Khairiah?
No, doktor.
Khairiah boleh pun buka ni okay je. Tak terkeluar pun Khairiah. So far so good?
Tak juga. But okay je.
Tak juga. Okay, tak juga. Okay. Let us just pray for her ya. Dia tak terkeluar. Faiz dah tanya Akasha.
Doctor, I wonder what makes the tubular and PFR difference because both is high.
You are asking what is the difference between PFR and tubular?
Yes.
It's the same thing. Tubular is just that we have the that orientation, but it behaves like a plug flow reactor. Okay?
Oh, okay.
All right. So it's the same thing. Okay. And again, this tubular boleh juga vertical ya. Tubular. Ya, tubular is also tubular sebab dia macam tu. For vertical, normally we have that when we put our packing. Yeah. And we can also assume it behaves like a plug flow reactor ya. Kalau dia keluar terus keluar macam tu ya. So can also be assumed like that way. Right, very good question Akasha. Asyik baik you tanya. Baru macam nak cakap. Takkan Akasha tak ada soalan.
Also about the first case for two reactant having reactant A and B, if we want to make both reactant having more higher possible concentration, then how do we do it? Because let's say we want to make A higher, then we have other two components, which is B and the diluent C. So how do we make A higher without making B lower?
How do we, are you asking with the question saying that A and B both are reactants?
Yes.
All right. So the question would be, how do we ensure the concentration of A is way higher than the concentration of B? Is that the question?
No, how do we make sure both concentration is as high as possible?
Okay. Easy as possible. Make it both pure.
Oh, make it
Then, and you fill in at a different streamline.
Oh, that is why.
Both
Okay.
pure. All right. Understand? All right. Very good. So we're going to take our first 5 minutes break. Yeah. All right. So let us take our break. Thank you. Okay, I'm back. So I'm going to proceed right away. And while waiting, I'm not going to wait for you to turn on your camera plus, but please do so, yeah? I'm going to just proceed with the next slide. So please responsibly turn on your camera. I'm going to proceed with the case number 2 for the parallel reaction having the two reactants. Now, in case number 2, the alpha 1 is greater than alpha 2. And let us go back to case number 1. Case number 1, the alpha 1 is also greater than alpha 2. It's just that both, yeah, the beta 1 is also greater than beta 2. But for case number 2, now the beta 1 is lesser than beta 2. So just go straight away to the equation of the selectivity, whereby we represent the first exponent at the Ca as small a, and the second exponent for the concentration of B as B. But then since B1 is lesser than B2, beta 1 is lesser than beta 2, so therefore now it becomes to the power of minus B. So if you, do I write it in the next slide? No, I didn't. So if we want to ensure that the selectivity is high, the K1 is high, K2 is low, Ca is high, but the Cb is low, yeah? Because now it is at the denominator of the equation. So therefore, the resultant requirement is the concentration of A should be maximized, the concentration of B should be minimized. So how do we do that? So which reactor scheme to choose, having high A and low B? So let us go to the next slide. There are 3 options that you can propose to have high A, low B. So let us have a look at the first proposal, which is by using semi-batch, where we have 2 different streams. The first stream feeding pure A initially. During the reaction, you feed in the A, and the A is pure. Then that will ensure that the concentration of A is high, yeah? In comparison to B, well, because we add the B later on, yeah? The B is added later on at the different stream, yeah? And the B is assumed to be not pure, yeah? In this case, we ensure relatively that the concentration of A is high, all right? The second proposal, if we choose tubular reactor having the membrane, so in this case, to ensure that the A is high, so you feed in as the inlet stream with the A, but the B is fed as side streams, yeah? The B is fed as side streams to the tubular reactor, all right? So it's again going to ensure that the A is high in comparison to the B. Now, if you choose to have series reactor, the same thing, you have 2 streams. The A being fed to the first reactor, then the outlet stream is added to the second reactor consecutively to also to the next reactor. And the B is added separately at the other reactors at different time. Yeah, so this will ensure that the A is started at a high concentration, yeah, in comparison to having the A together, yeah, with different feed streams, yeah. All right. So it says there, as you can read from the writings which I wrote at the bottom of the proposal, with A side stream of B continuously fed into the reactor. All right. The third one is A is fed only in reactor 1 and small amount of B is fed to each reactor. Again, that will differentiate the concentration would resulting the concentration of A to be continuously high because the A is fed in a small amount, yeah, to each of the reactor. All right. Okay, here the semi-batch, the B is fed slowly in a large amount of A, meaning why large amount? Because the A is in pure A and B is fed slowly, yeah, to the reactor. Meaning, in other words, it could be certain concentration but adding at different times slowly with a low flow rate. Then the concentration is maintained to be lower than the concentration of the A. Okay. All right. That would answer the question by Mr. Akasha. I hope that answers clearly now. All right, Mr. Akasha?
Yes,
Very
Doctor.
good. Okay, we're going to go to the next case, which is case number 3. Now the alpha is no longer greater than alpha 1 is no longer greater than alpha 2. It's now lesser, and together with the beta is also lesser. So we have the equation of the selectivity. That is the main equation, but the alpha 1 is lesser, beta 1 is lesser than alpha 2 and beta 2 respectively. Yeah, this one is lesser, that one is lesser. So both would end up at the denominator. In order to have high selectivity, so both concentration of A and B should be minimized. Yeah. Additionally, if we want to ensure that the A and B together are also at its minimum, then we can dilute it, yeah, with inerts. That is also one way. And if we are dealing with gas, then the pressure is also low. Yeah, that will result in a lower concentration of the gas A and gas B. Yeah? So we're going to go to the next slide showing you the possible proposal for the reactor scheme, yeah, having that condition whereby we want the A and B to be as low as possible. All right. Now we're going to choose CSCR because for a perfectly mixed CSCR, the concentration is always at its lowest. Then we have two different A and B being fed at two different streams, yeah, to the CSCR. That will give you low CA and CB. Then, of course, again, I repeat, you can dilute it with inerts. That would also reduce the concentration. And if you're dealing with gas, then low pressure. And that is for CSCR. If you choose tubular reactor, then one of the way is when you fit in A and B together. Here, in this case, if you have the feed stream coming in from a different feed stream, whereby you already have the A and B together, yeah. So that is why it is fed to the as inlet as one stream in a tubular reactor, but we want to ensure that the A and B is as low as possible. So how do we do that? So what we can do is the outlet stream can be recycled to dilute the inlet stream. Yeah. So that could be one of the way, yeah, to ensure that the concentration of A and B initially added to the tubular reactor is at its minimum, yeah, by diluting using the large recycle ratio, yeah. Take note that we have this heat exchange equipment to set at certain temperature, yeah. You will need to face all that later on. Now, the next case would be case number 4, whereby the alpha 1 is lesser than alpha 2, but then the beta 1 is greater than the beta 2. So we have this equation, alpha 1 is lesser than alpha 2. Now it becomes Ca to the power of minus A. Yeah. And since beta 1 is greater, then the alphabet B stays at the numerator. Yeah. So we have, in order to have high selectivity, the concentration of B is high. You need to set it as high. and the concentration of A is to be set as low. Yeah. So high B, low A. So how do we do that? So we have three proposals that we can choose from to have a high B, low A. So the first one is the semi-batch, high B, low A. So high, simply pure A initially added to the batch system, and A is fed slowly into a large amount of B. So that would ensure the concentration of B to be high, yeah, because A is added slowly. Secondly, a membrane reactor or a tubular reactor with side stream. So you want to have high B, so the B is added directly to the tubular reactor having the membrane, and the A is added at the side stream. Yeah, so that will ensure B as high as possible, A is low. Then thirdly, if you decide to run the production in a 3-series reactor, but with high B and low A, so ensure that the B is added. So please make a correction to your textbook 4th edition. So this stream should be B, yeah? B added B added to the first reactor, and with fresh A and B and A is added to each of the reactor later on. Yeah, so that would ensure the B is starting at the high concentration in comparison to the A. All right. So this is these are the examples of proposal that we can opt for different cases. Yeah. So we're going to go to the next scenario of still two reactants, but now having the effect of temperature whereby the temperature increases during the reaction. So it's an exothermic reactions. Now, for an exothermic reactions, during the reaction, the temperature increases. In order to avoid hotspots and runaway reactions, runaway reactions meaning maybe some of the reaction has certain limit, until it reaches certain temperature, then it may produce byproducts, your unwanted, more unwanted products. So in order to avoid that, we need to cool it down. So how do we do that? Yeah, one of the way is by using CSCR with a recycle. So meaning you have your A and B added to the CSCR. They react through time. As time increases, the temperature increases. So the outlet temperature for the reaction may be very high. Yeah, may be high. Yeah. So we want to avoid hotspots and also runaway reaction. What we can do is we can cool it down and recycle it. Yeah, cool it down, recycle it. So we have high temperature in the CSCR. So we want to reduce the temperature. We can use the cooled stream from the outlet stream being recycled. So that is one of the ways. Same goes to if you're using a tubular reactor. You cool down the recycle stream with the heat exchange equipment, then it will cool down your inlet streams, to a certain temperature. So that would be one of the proposed configuration that you can opt for if you are dealing with exothermic reactions. So if we have a thermodynamically limited reaction, for example, here we have a reversible reactions of two reactants, A and B. Forward reaction produces C and D. If at its equilibrium and the equilibrium state is disturbed, then it may choose to change direction. Instead of forward direction, then it could go in a reverse direction. When this happens, the C and D will no longer be produced, and then the A and B will now be produced. So in this case, we can say that it's a thermodynamically limited reaction whereby we want to produce as much as possible C or D. It depends on which desired products. But since it has a tendency to be reversed, then the production of C or D might be reduced. Yeah. It says that the equilibrium lies far to the reactant side. Yeah. And one of the product must be removed. Why is it reversed? Why is it reversed? According to the Lee Chatelier, the concentration of the C may be reduced, then it will change the direction. Yeah, and now will produce a correct. If the concentration of C, let's say C, yeah, if the concentration of C is reduced, then the equilibrium state will be disturbed. Then it decides to go in a reverse direction. Yeah. And when it is in reverse direction, we are actually allowing the A and B to react more. Yeah, the A and B now will further react and produce a C. So to allow more of the A and B to be used up or consumed, one of the way is to take out the C, yeah, so that it will go in a diverse direction and consuming the A and B, yeah, in the reaction. So this is what it means. So it is applicable when C has high volatilities. In this case, for a membrane reactor, we know that A and B produces C and D. So the C is in gas form because of the high volatility. We can simply take out the C out. Yeah. When you take out the C out, then it will allow the A and B to react more and produces more C. Because belah sini dah kurang, so dia akan pergi sana balik. Because bila C kurang, so dia akan pergi ke kanan, producing more C. So this is what it means. So the trick is take out C, then more A and B will react with each other. Yeah. All right. Same goes to the liquid phase. For a reactive distillation, A and B, then it produces C, which has high volatility. You push out the gas C, then the A and B would further react and produce a C. So that will be one of the way to cater the problem with the thermodynamically limited reactions. Kenapa dia panggil limited reaction? Sebab dia ada two direction. It can opt to go to forward reaction, the direction, or it can opt to go to a reverse direction. So the production of the product belah kanan tu berkurang lah sebab sekejap kanan, sekejap kiri, sekejap kanan, sekejap kiri. So what we want to do is, the trick is kita nak pergi ke kanan je banyak supaya C tu banyak produce. If we choose to have C as your desired product, yeah. So what we can do is, once C produce, take it out, then the thermodynamically dia faham, alamak C kurang lah, so dia akan pergi kanan. C kurang lah, dia akan pergi kanan. Meaning dia terpaksa consume A and B more to produce C. So this is what it means, yeah. Do you have any question? Ada soalan?
Doktor.
Syafiq? Ya, Syafiq Abu. Betul lah saya panggil Syafiq Abu. Rupanya dia ada soalan. Ya, Syafiq Abu.
Saya nak tanya, what if kalau C tu dia bukan higher volatilities?
C bukan higher volatilities, ya. Okay. Kalau C bukan higher volatilities, C would be in the outlet stream together. Alright? Here, kat sini.
So
sama
kita
juga.
tak
C
boleh...
dia tak boleh juga, because dia ini hanya example lah. We can have, kalau ini membrane, so this is not membrane, ya. If this membrane, there are many kinds of membrane, ya. Membrane untuk separate gas, membrane untuk separate liquid juga. The trick is, for gas senang saja, yeah, because gas and liquid, so it's easy, yeah. So you separate the gas and liquid through membrane. But then if you have both liquid, like question Syafiq Abu tadi, how do we use membrane? So you have to choose the right membrane depending on maybe the pore size of the liquid ataupun the molecular weight, ataupun kalau liquid, most probably the molecular weight, a specific membrane which can separate two different components which are both in liquid phase. Yeah. So kena design betul-betul yang specific for that. In this case, dia hanya bagi example yang kalau high volatility senang lah. So you can easily ensure that the liquid here, then the liquid also goes out from the outlet stream. Then just simply take out the gas form through the membrane. So dia keluar melalui sini. Yeah. For the second one, here you have A and B. Let's say liquid, dia dua-dua liquid. So tak adalah purging C at the top of the tank. Yeah. Why we have this C taken out from that tank? Because it's lighter. Yeah. It's gas form, high volatility. If you don't have that condition, even if you purge out, tak ada apa yang keluar lah. So what you see is at the outlet stream, you have both C and D. But then if you opt to help this thermodynamically limited reaction, you nak kena take out ni, so you have to go through certain separator kat sini, take out that C, yeah. Most probably we can do that, yeah. Or maybe it's not possible, yeah. So we have to creatively think of the best design to manipulate the thermodynamics condition. Right? Do I answer that, Mr. Shafiq Abu?
Thank you, Doctor.
Yeah, okay. If I don't, then we can discuss further. Then if we have other examples, then we can share together in class. Yeah, all right, Shafiq Abu?
Okay.
Okay, whatever, so just take note, whatever that you have in class, hanya examples. There are so many creative design, complicated designs which are also available, which needs to be proposed or designed specifically by the engineers. So basically, apa yang kamu nampak ni hanya the most common examples seen for so many years. Yeah, so we use that as our knowledge as reference. But through time, that knowledge enhanced and also added, from day one, from day by day, So some of the things which are not in the class, meaning we are going to use our creative design knowledge to help the newly problem that we face, something like that. Okay.
Okay. Thank you, Doctor.
We're going to go, yes, no problem. So we're going to go to the next slide. So this is the most interesting part, whereby you also need to grasp the skill of predicting the concentration profile. When I say concentration profile, meaning you have to have the ability to foresee what would happen to the concentration, for both the reactants and also the product. So we may have to be able to predict the concentration profile through time. So the X is always time. And there are many reaction types, as you can see here from the first slide, then we have second slide, that will be the last slide, as example, which are taken from Levenspiel. So from the previous slide, I wrote it Fogler, so please correct it. It is taken from Levenspiel textbook, So we're going to start. We have 5 cases. We have 5 different scenarios. Let me number it. The first one, this is the first. There is second. There is third, fourth, and finally fifth. So we're going to go to each one of this slowly and carefully so that we can understand that finally, at the end of the day, you should at least have an idea of how to predict the concentration profile for both the reactant and also the products. So let us start with number 1. Here, okay, before we start with number 1, I'm going to make an overall comparison of what we're going to have, of what we're going to analyze, First, we have one reactant. Both of them, not both, all of them have one reactant. So the fifth one is also one reactant. All of them go through 2 pathways. pathway number 1, pathway number 2, either irreversible, both are irreversible for scenario number 1. For scenario number 2, one is irreversible, the other one is reversible. Scenario number 3, both pathways are reversible. Scenario number 4, both pathways are reversible as well. So what is the difference between scenario number 3 and scenario number 4? So take note, we have numbers there for each of the directions of the reactions. For the reversible, here, scenario number 3, all are written as 1. So we say that the intensity of the specific rate constant, the forward reaction and the reverse reaction for both pathways are the same. In comparison to scenario number 4, we got 3, yeah? Have a look at that. 3. So it is saying that the intensity of the specific rate constant, for example, or the reaction rate, for example, is 3 times higher than case number 3 or scenario number 3, yeah? For both forward and also reverse. But for pathway number 1, both are the same, 1, 1, 1, 1, all right? So let us look at scenario number 5. So the small one is scenario number 4. This is just to compare between 4 and 5. So what is the difference between 4 and 5? The 4 we have 3. The 5 we have 10. Instead of 3 we have 10. So meaning the intensity of the rate of reaction of the specific rate constant is way higher, yeah, than the previous scenario, right? Both of them have reversible reaction for both pathways. All right, so I'm going to go to my previous slide. Here, I'm going to start one by one. So we are going to imagine what would happen to the reaction by predicting the concentration profile. By right, how do you get these curves? So normally these curves are proven experimentally. But from the knowledge gained for many years about chemical reaction, we can already use the established knowledge to predict our concentration profile. Yeah, so this is what you see. Yeah, we know that the A produces R, the A produces S. Both have the same intensity of the rate of reaction, let's say. Yeah. So we can say through time, the A as the reactant will decrease. All right. So I'm going to use different pen color. Let's say blue. So the A will decrease. It's very clear. At the same time, through time, the product will increase. So since both R and S are at the same intensity of rate of reaction, let's say a specific rate constant and so on, then we can say that they are having the same curve. Yeah, just to predict approximately. Yeah, reaching at certain level at the end. Yeah, so we have decreasing A and increasing product R and S. Okay, for parallel reaction, assuming for an elementary reactions. Clear? So we're going to go to scenario number 2. Now, the first pathway is reversible. The second pathway is irreversible. And we know that through time, the A will decrease. Okay? And the S will increase, correct? So let's say there is your S. The S will increase because it's a product. And we also have the second product, yeah, which is the R. The question would be, how would the concentration level of the R in comparison to S? Should be higher or lower? Logically, since it is reversible, sekejap ke kanan produce R. Tiba-tiba ke kiri pula tak produce R. So logically, due to that, the R concentration is lower than the S. Let's say there is a time, yeah? the R concentration is lower than the S. The S, once you have A, produce S je. Through time produce, you increase. But the R increase. Kenapa kita pilih bawah? Sebab sekejap dia akan ke kanan, sekejap ke kiri, ya. So bila dia ke kiri, dia kurang. Ya. So this is what happens, ya. This is what happens according to the Lee Chatley's. Because bila dia go forward, A produces R. Then when A reduces, because R dah banyak, so dia patah balik. Nampak? Okay, so it's a balance between the increase of R and the decrease of R with the decrease of A. But still we know that the concentration of R is lower than the concentration of S because S is being kept continuously produced, but not the R. R due to the reversible reaction. Can we proceed? Boleh? So I'm going to go to the third scenario. Both are reversible. So we know the A decreases. But since both are reversible, then the R and S have the same intensity there for both pathways, reverse and forward. Then we could say that towards the end, the reactant and also the product will achieve a certain equilibrium state of the concentration. Yeah, so that would be scenario number 3. But now, for scenario number 4, both are reversible. All right. So we know that the A decreases, but then I'm going to delete these writings where you can see clearly. Okay. Can you see that clearly? Boleh tulis tak? Again, kalau saya delete ni, saya kena escape dulu, keep, then reshare. Hold on. Okay, I'm going to share that. Okay, so we're going to have a look at the fourth scenario, yeah? Both are reversible. I'm going to choose blue color. Erase that. I'm going to choose blue color for pen. Okay, both are reversible. But the first pathways has higher intensity in comparison to the second pathway, yeah, producing the S, yeah, in comparison to R. So we know that even though the S, and not even though, we know both are reversible, so we should end up seeing that the R and S would be in equilibrium at certain concentration since the R is higher intensity. So the R would finally reaching an equilibrium with the S. And the S concentration is way lower than the concentration of the R. Yeah, because the R has higher intensity, yeah, of the rate of reaction or specific rate constant. But then we know that through time at earlier stage, definitely the R will increase, then it will start to decrease due to the Lee Chatelier, but still at higher concentration than the S. Yeah, the S will keep increasing. Yeah, then at certain level it will reach an equilibrium with the R. All right. The A is clearly going to be decreasing. So that would be the concentration profile for both reversible reaction. Okay. I'm going to go to the last one. Let me, I cannot erase. Cannot erase. Tak boleh erase. All right. I'm going to choose again blue. Now we have A decreasing. We have R way higher intensity than the first R here. So way higher in comparison to just here. So it reaches higher concentration of R even at the earlier stage of time. Yeah, time in comparison to here. At earlier time, the concentration of R is already very high. Yeah, but it still will start to decrease due to the Le Chatelier and finally reaching an equilibrium with the S. All right, so that would be the last scenario. Okay, do you have any question? Azri?
So far,
Okay, Hanani?
Um, tak ada.
Tak ada? Najwa?
Tak ada, doktor.
Afifah?
Tak ada, doktor.
Not yet. All right. Tadi siapa yang kata not yet? Bukan Afifah yang tadi? Afifah kan? Belum, bukan. Siapa yang tadi not yet? Not yet. Siapa yang not yet? Cepat angkat tangan. Lupa pula. Hanani Hanani, you ke?
Bukan. Alia Karina
Bukan,
tak silap saya.
Oh, Karina. Siapa? Karina. Oh, Nuraya. Dah ada question belum? So, that will be the end of the the second part. We got a few more minutes. I'm going to touch a little bit on the third part. Yeah, can we do that? Can we do that? I'm going to stop till the last two slides. Yeah, the first slide here and the other slide. Sorry, the first slide here and the other slide here for the remaining time. Just bear with me, okay? So we're going to touch on the series reaction. So earlier we talked about parallel. Now we're going to look into series. So when we have series, always remember we have intermediate, right? And it's just to say that the intermediate now is your desired product, meaning dia duduk tengah-tengah. So once you have your desired, then if it choose to go to the right, it's a series reaction. The nature, by nature, then it will produce another product, which is the undesired, unfortunately. So the question would be, how do we handle this kind of situation? What we want is to maximize the D, yeah? Not so much of the U, yeah? But once you have the D, then it by nature, it will produce U, yeah? With KU, yeah? So we have the specific rate constant of KD for the first pathway, the A to D, then once you have D to U for the second pathway, yeah? With the KU. And I just simply show that there are two kinds of presentation that we have seen earlier. Yeah, in this topic 6, we use KD and KU, but earlier in our previous topics, we used to use A to B and B to C. And the specific rate constant is simply the K1 for the first pathway and K2 for the second pathway. Just to show you here, is both are the same. Yeah, it's just that we specifically make it more specific, saying that the B now is your desired, which is the intermediate. All right. So having that ability to predict the concentration profile, so we have the concentration and also time. In a series reaction, the A will produce D, the D will produce U. So we now know that the A will decrease until it reaches a certain level, which is no longer that we have A. Since the D is the desire, which is B, yeah? In this case, we are writing it in terms of A, B, C. The A reduces till it's no longer there. And the C will keep increasing, all right? But what happens to the B? The B, it will first increase, yeah, because we only have this A to B, so A to B, A to B, A to B, A to B, yeah? And then until it reaches certain level, the B now allows the C to keep increasing higher and higher, yeah? So relatively, the C is higher and higher. It produces C higher and higher. Now the B is reducing. So this is what it means. Yeah. Yang first part ni A to B. Second part is B to C. Alright. Of course, at the same time, here daripada sini C is already being producing, yeah, being produced, but gradually, yeah. So that is why you see the D is gradually increasing. Sampailah at one position, it keeps increasing and the B reduces. All right. Okay. So the next slide. Sorry. Mana next slide? Oh, saya tersilap. Saya skip. Patutnya kita predict the concentration profile later. But anyway, this slide shows you on how to write the rate of reaction. Yeah, there are two kinds of rate of reaction: rate of disappearance of the limiting reactant and the rate of formation of certain product. Right? Now, take note slowly. We have series reaction. The intermediate is the B, yeah, or the D. So let's choose this one. Yeah? So if the A produces D, so we are talking about the rate of disappearance of the limiting reactant A. So how do you write it? Simply the K times the C. C of what? C of the reactant. The K of what? K. So since here we write KD, then it's KD times CA. Same thing is if you use this one, yeah? So simply K1 times CA. Simple as that. Now, if we see D producing U, now the D is the reactant. So simply the rate of disappearance of the reactant is simply the Ku times the CD, which is the reactant. Same goes to here, K2 times the reactant concentration. When we talk about the rate of disappearance of B to produce C. Okay, clear? Now, if we want to write the rate of formation, so in this case, we are talking about maximum production of the desired product. Yeah. So we write it in terms of rate of formation of D. So I'm gonna erase this. Sebab saya nak scribble lagi. Erase. Saya nak scribble lagi. Alright. Lepas tu, dia tak bagi saya ni, saya keep dulu. Then I'm gonna reshare. Then only I can rewrite. Okay. Now, we want to write the rate of formation. I'm going to use blue color. Rate of formation of the desired product, which is the intermediate. So how we do that? To know how much D is produced is simply dKd times the Ca. Right? So that is the rate of formation. Okay? Now, to know how much D is produced is simply, okay, we have, of course, from here we know D produces U, yeah? Yeah? Having Ku times CD, correct? But now we want to focus on the formation of D, so it has to be reversed. So simply adding negative. So it will give negative Ku times CD. As simple as that. Same goes to here. We are focusing on the B. simply the K1 times CA. Yeah, we are focusing on the B from C. Yeah, but we know that if we want to use the K2, yeah, we know that K2 times CB, yeah, producing C. Since we want to focus for B because rate of formation of B, so simply add negative. All right? Okay? All right, so very good. So that would be the next slide, which we have discussed earlier. And the next slide would be some of the fundamental questions that we can answer if you understand it well. So I'm going to give you the time to do that in the next lecture. So we're going to stop our lecture today here. And we will meet again in the next lecture and continue with a few questions and how to fundamentally cater the answer, yeah, for each of the questions here. All right. So hopefully that we could see again next week. And last round. Shafika, apa jadi Shafika? Where are you? Nonada, okay. Akasha, Fazlika. So Najwa, I'm gonna ask every one of you to write in the chat box your level of understanding, excluding yang baru nak hadam for today's lecture. All right, can we do that now? So it can be any numbers, yeah. There's no penalty for anything. This is just for my reference. Okay, Nornada, 45%. All right, 45%, 5% bagaimana? Tak tahu Nornada. Maybe kelas petang. Alamak, Karya 40%. Okay, mine is 57. Manalah tiga ni pergi ni, Alia. 57%. All right. 50% Adriana, that is normal, yeah, 50%. Kalau bawah 50% tu, I should worry. Syafika, alamak, 40%. And 55% Shadiana, 45% Afifa. Okay. Mana 55% ni sama macam Nada. Dan Azra 50%, Camelia 50%, Anis 45%. Banyak hilang 5% ya. I think roughly I understand everything just on surface. Yeah, sounds like 50%, I guess so. 50%. Can I say 50%? Yeah. Akasha boleh Hanani. Hanani above 10 on the surface lah tu. 60%. Hanani. Then Nabiha. Hanani lah tu. Azwan. Allah. Azwan. 49.99%. Okay. Belum cukup pure. Ya. Tak cukup pure 50%. 49.99. Yeah, close. Okay. Where does it go actually? Fazlin, 55%. Ya, Alhamdulillah. Fazlika, 55%. Faiz, 40%. 40%. Daniel, 44.44%. Daniel, okay. I wonder how. 40% Shafi, Iman, alamak Iman, 43%, but a little bit higher than 40%, okay. 45% Amani, kemanalah hilang 5%, Najwa 50%. Thank you for your cooperation in answering this. So at least with kelas petang ni dapatlah dekat-dekat 50% tu kira Alhamdulillah lah ya. Alright. So congratulations to all of you. So we'll meet again next week. Not next week. In the next class and we'll try to finish it up and try to have a look at the ODE solver. Alright, in the next class. Alright. Assalamualaikum warahmatullahi wabarakatuh. Bye.
Thank you,
Waalaikumsalam. Thank you,
Doktor.
Thank you,
Doktor.
Doktor.
Bye.
Yeah,
Thank you,
thank you, Doktor.
Welcome. Bye-bye.
Thank you, Doktor.
Bye. Masyita tak nak keluar ke? Benda dia fikir. Oh, dia cakap siapa tu? Mesti buat benda lain ni. Apa Masyita buat tu ya? Masyita, buat apa tu? Dengar tak I cakap? Tak dengar lah tu, you off speaker. Dalam kelas tadi you off speaker tak dengar I cakap Oh, dia off. Okay. Sampai ke sudah tak keluar-keluar. Apa benda lah dia duduk tepuk-tepuk. Apa benda muka dia duduk tepuk-tepuk kepala. Cakap seorang-seorang.